Boom, on. Oh, that's not the one. Oh. Okay, we might be onto something here. Oh, everyone on YouTube's like, yay, we can hear you now. And then they said like, oh, it stopped again, but is it going now? They're on a 30-second delay, so I gotta wait a few seconds before. Do we have anything? Oh, I think they're giving me the thumbs up. Give me the, like, is it working? Then we have to wait for 10 seconds. Yes? Oh, they're saying we can hear you and the music. Okay, so running the cable worked.
Nice.
All right. And because I'm now on YouTube, I have to use like non-copyright music. So
Yeah.
so no more Pandora, no more Amazon Music. I had to subscribe to one of those music services. Otherwise, YouTube just goes. Sorry. I like the test I did. Actually, no, I had audio on the test I did last time, so I wonder why that didn't work, because YouTube said, sorry, that that stream contains copyrighted music. And all right. Hey, I like this. So the reason why I'm doing this on YouTube is I had a student yesterday tell me that because he lives out in a rural area, his internet service is not that fast. And so he can watch live, and then Zoom will downgrade the quality appropriately. But if he wants to watch offline, he has to download the video file, and the video file is at full quality. So he said to watch the 1 hour video file, it took him all night to download it.
Dang. That sucks.
Yeah. So I said, well, maybe we can do something with YouTube, because YouTube will, of course, adaptively change the bitrate.
Yeah.
To match what you can download. He says, I'm fine watching a lower resolution or a smaller one. I just need to be able to watch it like without it buffering constantly.
Yeah, yeah, that makes sense.
So we're trying this. So people on YouTube, the people you're hearing are my live students on Zoom. Oh, so if you're wondering where I've been the last 3 or 4 years, it's because, well, COVID hit and I went all online. And so I've just been using Zoom up till now. But like I told you the story just a moment ago, that I have some students who want to watch me on YouTube because they need to be able to watch at a lower bitrate. Is there somewhere else I post content? Yeah, on Zoom. It's just for my students. So you're hearing their voices. I'm seeing their faces, because on Zoom I can see their faces, but you're just hearing their voices. All right. Oh, so that was 10 minutes of debugging and stuff like that. Well, I'm glad I got that cable connected, because my goal was eventually to connect that cable. I just didn't think I would have to do it today.
Yeah, that's neat. There is an echo when we talk. It's a really, really slight, very small echo.
That totally makes sense.
Maybe.
Where are you talking, on YouTube or
On Zoom, right?
Yeah, yeah,
I'm
on
not
Zoom.
hearing any echo.
Occasionally, I get like when I say something, if it's quick, I get a really quick.
I'm sure that has to do with the
small
way
echo.
I'm mixing all the audio in, right? Because
Yeah.
because the Zoom is coming from you, and then it should only go to me. Your audio should go to me, but because of the extra cable I just hooked in, right? So the
Yeah.
Zoom audio is going back out into my mixer and then back into Zoom again,
Yeah.
but delayed by
it's-
a little bit.
Right. And it's a really quiet, like I can barely hear it.
Well,
So it's not.
hopefully we can put up with it today, and then
Yeah. Yeah.
I will debug that over the weekend. Right?
Yeah.
That
It's
has
so
to do
light
with
that.
creating more channels on the mixer, and
Mhm.
right,
Yeah.
that includes this audio but not this audio, and also
Yeah.
making sure that the audio that feeds back into my video mixer. Actually, ultimately, what I want to do is I want all the audio to go through my audio mixer to separate out the different tracks, so that I hear a different thing than what you hear.
Mhm.
Like, I don't want to hear myself.
That makes sense.
No, actually, no, that's not true. I want to hear myself because if I don't hear myself, I tend to yell, right?
Oh yeah. I can see
Oh
that.
yeah,
But-
same here.
But what was it? There was something I didn't want to hear, so that's why I created those separate tracks, so that you hear stuff that I don't hear, and I hear stuff that you don't hear. But ultimately, because of the latency issue, you've probably noticed that on Zoom, like, my audio comes in faster than my video.
Mhm.
So like my audio is like 1/10 of a second before my mouth starts to move. And that's because the latency through the audio mixer is a lot shorter than the latency through the video switcher.
Yeah, that makes sense.
The video switcher introduces about 1/10 of a second lag, and the audio mixer is like almost instantaneous. It's a little bit of lag, but not so you notice. So because the audio is coming to Zoom faster than the video is coming, it's out of sync. So what I need to do is actually take the audio out of the mixer and pass it through the video switcher,
Okay.
so that it all has the same latency.
Mhm.
And so running that cable is eventually what I was going to do, but now I need to rejigger all the audio tracks
Yeah.
because now everything's coming to the mixer, and I only want some of it to go through the audio or the video switcher. Everyone's going, please release more videos on YouTube. I've been doing this for the last 1.5 years, and I'm going to be doing this for the foreseeable future, because our lovely dean has basically is going to put in a request every semester for the foreseeable future to just have us continue doing online, because we just get gangbusters enrollment on online. I mean, we do have students who want to do on ground, certainly, and we'll offer on ground classes, but they are just far dwarfed by the people who just want to do online. So over the next
it's
year,
more
we're
convenient.
going to roll out more on ground classes over the next year, but it won't be. We may never ever go back to the pre-pandemic levels, which actually would be great for our classroom, because our classroom was just being like scheduled solid from 8 in the morning until 3:30 in the afternoon, just back-to-back classes. Maybe now we can get a little break in there.
Yeah, I prefer online. It's just being able to turn back time on a video is something you can't do.
Yeah. Oh, well, the nice thing about the YouTube is you can roll it back if you want.
Mm-hmm.
Yeah, so we've got one of our normal students on YouTube. That's great.
Cool.
Someone who's normally here, whose picture or icon at least is normally on the Zoom, is on the YouTube.
Oh, is that Brian?
No, it's John.
Oh, okay, yeah.
So, hi, John. Okay, so where did we leave off last time?
I don't know. I
Oh.
unfortunately had to leave early.
Oh, that's right. We
Yeah.
had to leave early.
Stuff about files.
Stuff about files.
Command
So-
line arguments is one of the
Command line
things.
arguments. Yeah. So we started talking about files last time, and I need to create my.
Last thing I have written down is about the P error messages.
Oh yeah.
You showed us something about how standard error superseded the our output in standard output.
Yes. Oh, it's all coming back to me now. Good. I'm going to turn off the music. Just when the song is over, I'm going to turn it off. It is nice to have the background music, though.
It is.
I went crazy on Epidemic Sound last night, like tagging songs. Going like, I like this one. I like this one. I like this one. I like this one. Actually, if this YouTube thing works out, my goal is to. I'm giddy with excitement here, right? I've got intro music like this, deep house, get ready, and then the goal is like right before the stream starts, I switch over to like happy, like rev it up music, and then when we take the break, I've got intermission music. Right?
That's cool.
Oh, let me see. Here's the intermission music. Here's one.
Like saloon music. That's awesome.
That's one. And then like right before the stream starts, you do this one.
Yeah.
Wouldn't it be great if there was an API for this service here so that I could basically have a program time it out for me? Say like, okay, the stream's going to start at 9:30, so whatever song you pick for this like pre-stream sound, start it. Let's say this sound is 3 minutes and 10 seconds long, right? So start it 3 minutes and 10 seconds before 9:30. So start at 9:26 and 50 seconds, right? And then back out all the other songs, right? So we know exactly when to start the song, so it will finish. That song will finish exactly at 3 minutes and 9:26 and 50 seconds, and then boom, this sound starts, and then boom, stream starts at 9:30.
That'd be cool.
That'd be cool. Oh, I hear the echo now.
Right?
Yeah.
When you turned off the sound, it got real bad.
Yeah.
Or the music.
Maybe
It's a sign you should let the music play the whole time.
The music turn on, right?
Yeah.
That might. I wonder if it's just covering up the audio, the echo, or it's actually kind of like curtailing.
Getting rid of it.
Yeah. So. Yeah, I'll just make it real quiet. I don't remember if we already played this song, so we'll just do it again.
Yeah, as soon as you turned it on, I still have a really small, quiet echo, but your echo's gone.
That's cool. Yeah. I have no idea why that happens.
I don't know either.
But you're right. The echo just goes away once the song is there. All right, another thing to debug.
No, that's part of the song.
Yeah. That's funny.
Where do I get the songs? So Epidemic Sound. John, is this a lecture for CS26? No, this is 46. Okay, so we left off with files last time, and I wanted to leave you with this kind of picture that a file is this. Kind of like an array of bytes. But how does a file differ from an array as far as how you access it?
I don't think it would it? I mean, when we did the other file, when we did the picture file, it was...
So an array is random access. I can ask the array, or I can pull a byte out of the array here, and then a moment later I can pull one out over here, and then I can pull one out over here, right? So I can just go to any point in the array. Is that different from a file?
File is sequential, so it has to go from 0 to end.
Yeah, file is sequential, so you start at the beginning and you work your way towards the end. I mean, you can randomly access a file using some different functions to move around the file, but it's slow compared to an array. So for all intents and purposes, a file is sequential access. You start from the beginning and go towards the end. And so when you open a file, using what function?
Fopen?
Fopen, you get this file structure back, all capital letters, and it's a pointer, so it's pointing to this thing. And inside of that structure is information about the file that the operating system needs to be able to keep track of the file. You've got things like the mode of the file. Is it read? Is it write? Is it append? You've got a space set aside called the buffer. This is used to hold a block of data. Remember, files, at least modern ones, stored on modern storage devices, are composed of blocks. Each block is about 512 bytes long. You dealt with that in your CSI assignment. So when it reads a block off the disk, it holds it in this buffer. And then when it writes data to the disk, it takes the entire buffer, the entire block, and puts that all on the disk all at once. So the computer actually can't read and write single bytes to the file. It has to write in blocks.
Okay.
And then it also contains the offset. The offset is how far into the file are you currently. So basically you can think of the offset as pointing to where you currently are in the file. So it keeps track of where you are so that when you write another, essentially write another byte to the file, that offset moves one character over. So it's moving towards the right, moving towards the end of the file. And the reason why files are arranged like that is historical. It has to do with the way files were stored way back when computers were new. We didn't have disk drives. I say we, as in like computer users. We didn't have disk drives. We didn't have SSDs. What did we have before?
Tapes.
Tapes, yes. So we had things like, hold on, tapes. Right? This is a spool of magnetic tape. It's about 1/2 inch. If you unsnap this, this comes off, and then, oh, it's taped. It's taped down, so I have to untape this. The tape is taped by tape. Right, but here it is. This is a strip of magnetic tape. This is not unlike the magnetic tape you would have found in an old cassette. You know, the old cassette tape, audio cassette tapes from the 1980s and 90s. Those were really thin, right? There was only about 1/8 of an inch thin. These was about 1/2 inch. So they can, because they're thicker, they can be spun through the machine faster, and you can kind of hold a higher density of data on here. However, you know, a tape like this is it says here, 800 bits per inch. So
wow.
every inch can hold 100 bytes of information on here.
Jeez. That's funny.
I don't know how long the tape is. They came in standard lengths. I don't offhand know how long this tape is, but if you knew how long it was, you could calculate the total storage capacity of this.
Mm-hmm.
But this is the reason why files are sequential, because you can't randomly access information on this. You have to physically roll the reels to get to a certain spot on the disk. And even when you're rolling the reels, you still have to read the data really fast to keep track of where you are, so you know when to stop. Right, so that's magnetic tape. Oh, John on YouTube says, I'm going to take off because he's not in this course. He's in the other course. Hey, John, stick around. You get a leg up when you do take the course. Before there was magnetic tape, there was paper tape.
Mm-hmm.
I don't know if the camera can focus on this, but it's about 1 inch wide. Can it focus? Come on. I gotta obscure my face. If I obscure my face, then hopefully it'll focus. There we go.
There it is. Yeah.
It's about 1 inch wide, and if you count the holes, there's 8 larger holes and 1 smaller hole. So 8, of course, it's a byte. It's 3 on one side and 5 on the other. That helps you know if you put it in backwards, right?
Okay.
Right. So you can't accidentally put it in backwards. And then the smaller hole, which is this line of holes going roughly down the middle, that's that's basically telling the machine where each row of dots is going to be. So if it knows that it's looking at the hole in the middle, it knows there's going to be holes to the right and left it needs to read. So it's basically keeping track of where the data is.
Mm-hmm.
And it also it's helped to align it, right? You make sure that the hole is on this side of the tape, not on this side of the tape.
Yeah, that's neat.
So this would have held, I think it's labeled on here, this holds an operating system of some sort from 1976. Again, I got to cover up my face in order to get it to focus. Yeah, 1976?
Wow. So that's an original one.
Yeah.
Dang.
So what would be some advantages to using something like paper tape?
Magnet won't mess them up.
Yeah, so not magnetic, so magnet won't mess it up. What else?
Other than that, maybe you can't overwrite what you've already done by accident, but I don't know.
That's true. You're never going to overwrite anything on here, right?
Yeah.
This is write once. That could be an advantage for something like an operating system, right? You can't change the data on here. There's one I can think of is with like the magnetic tape, right? I would need a machine to read the data off here.
Oh yeah, with that you could just look at it
With
and
this,
count the bytes.
I could physically just look at it. I mean, it would take a long time, but
Yeah.
I could just physically look at it and get the data off of there. And it wouldn't be that difficult for me to construct a machine that just simply like had 9 light sensors on it.
Mm-hmm.
And every time the middle light sensor registered, it would just read what's off the other 8. And I could get the data off of here fairly quickly, fairly inexpensively.
Mm-hmm.
And of course, we can think of a myriad of disadvantages, like what if it gets wet?
Yeah.
What about a fire?
If it gets torn.
But I do have other examples of storage. Like this here is another tape cartridge.
Mm-hmm.
620 feet of 1/4-inch tape. And then here, this is in a nice, strong case. So you would slide this into a machine, and what it would do is it would open up this door right here. And then it could access, I don't know, can you see that? It would access the tape, which is right there.
Yep.
And the reason why it's in this strong case is that now, with a nice durable backing, it can spin these reels really fast.
Yeah.
So that's it for like the tape stuff. And then I have here, this is one of my best things in my collection. This is super old. This is not a storage device. I mean, this is RAM.
Wow.
I gotta hide my face in order for you to see that. Come on, focus. There we go. Can you even see it?
Holy cow.
What is
Yeah,
it?
yeah.
What is it?
Those are the little beads.
Yeah, these are the magnetic cores.
Dang.
Each one of those magnetic beads, which you can barely see in this video,
Yeah.
right, is a bit. And I'm going to guess, just an estimate, there's probably 1,024 on here. That's
How old is that?
Oh gosh, this would be from like the 60s, I'm going to guess.
Wow.
You know, so it's kind of like a fabric. And
Like,
Yeah.
I got 1K RAM.
1K bits,
Oh yeah, not even 1K. Wow.
1 kilobit.
Yep.
You know, so back during the war, actually this was probably in like 50s maybe. So back during the wartime, they actually hired weavers
Mm-hmm.
to come and make these, right? Because someone's got to use a needle and run these thin wires back and forth through this thing. They're all handmade.
Wow.
Okay. Need to set it aside. And then, hold on, where's my box? Oh, here's my box. And then you stack them up into a module like this. So each one of these boards here is one of those things.
Yeah.
They're protected by boards on the other side of them, but if you can look in, there's the core memory in there. And if you count these boards, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So if each one of these boards is a kilobit, then 8 of them makes a kilobyte. 1 kilobyte of memory right here. And this is the kind of memory that's flying through space right now on the Voyager spacecraft.
Jeez.
Way out beyond, the orbit of Pluto.
Yeah.
This kind of stuff. Not only because, the core memory was long gone by the time Voyager launched, but the reason why they use it is, well, first of all, Voyager was probably designed back when this was state of the art. But the other is, this is almost impervious to cosmic rays.
Yeah, I can see that.
They're physically big enough that one cosmic ray is not going to cause it to just flip a bit.
Yeah.
Whereas today's memory, the cells are so small that one cosmic ray can cause an error in bits. Are you all enjoying this? Looking at
that's neat.
this old stuff. And then
It's one thing to conceptually think about it, but actually seeing it, that's neat.
this here is, now this came out, I'm going to guess, in the late 80s, early 90s. It's basically an optical disc inside of a cartridge, right? And the reason why it was in the cartridge was they didn't want people to put their grumpy fingerprints on them.
Yeah.
Right? So it was safely held in this cartridge. When you stuck it into the machine, it would open up this door, kind of like on a standard floppy disk, right? You've seen that little shutter that moves to the side, and then it could read and write the data. But this is, if I can read this here, this is a write once optical disc. You can write the data once on here, and then that's it, right? Once you've written it, that you can only read from it. And back then, I remember when these things came out, people went, that is the goofiest thing ever. Like, why would you ever want to write something once? It'd be like for government documents, right? You write the government document to this once, and then you just throw it away. This is the way government works, right?
Yeah.
Is it so goofy anymore?
Nope.
No. I mean, up until just recently, you remember those stacks of CDs, CDRs, and DVDRs you'd get, right?
Yeah.
Right? Write once, and then throw it away when you're done.
Yeah.
So this was called a worm. Write, WORM. Write once, read many times.
Oh yeah. That's funny.
Yeah, back then we were just like, that is the weirdest thing, right? What's next, read once, write many times? And then these were very short-lived.
I remember those.
No, this is a floptical.
Oh.
Come on, focus. I get in my face right there.
Oh yeah, okay.
Whoa.
It's
21.
21 megabytes.
21
So
megabytes.
It's the same
Yeah.
size as a standard floppy disk, right? Exact same size, but it's got this magnetic optical. You can actually, if I hold my face up to it, you can see through it.
Yeah.
Right, magnetic. It's optical media.
Wow.
21 megabytes. That was astounding back then. On in something this big.
Well, yeah, because the 3.5 floppies were
1.4
What?
megabytes.
Yeah.
So this holds like 15 times as much.
Yeah.
It's incredible. I think they were on the market for like a year. And then I have more stuff, but I got one more thing to show you. But this is a SciQuest cartridge. This is basically a hard drive platter inside of a case.
Okay.
So can you, there, you see those hard drives back? I got them opened up right there. So it's basically, it's a 5 1/4 inch hard drive platter in a case. And, you slide into the machine, and then the read-write heads would go into this cartridge and read the data off of them. They were state of the art back then, 44 megabytes, right? You're basically carrying around a hard drive.
Yeah.
But part of the problem was you couldn't store more data on there because this is out in like the dirty environment, right? You just open this door and suddenly dirt and stuff can get in. That severely limits how much data you can put onto it because it has to have kind of like the large enough memory cells that a piece of dust is not going to affect it.
Yeah. Good for backup, though.
These were backups mostly. These were out for 10 years or so. They went up from 40. They started out at 44, then they went up to 100 megabytes, and then 200 a giga. They topped out at like a gigabyte or so. And then one more thing. Well, two more related things, right? So you've seen.
Oh yeah.
The 5 1/4 inch floppy disk.
Yep.
Right.
I remember those when I was a kid, when I was in like I think first grade.
Yeah.
We were using those to learn how to type.
Oh.
Yeah.
Like on one of those old dot matrix machines, like an Apple with like just a green pixel and a black background.
Yep.
Like 1995.
Yep.
But before there was 5 1/4 inch floppies.
Yeah, the big ones.
The 8 inch.
Jeez.
I mean, you probably can't tell on camera that they're really a different size. Right? You can barely get us into the monitor, right? It's so big.
Everything just gets smaller and smaller. That's like the Nintendo Switch.
Yeah.
Right? We got that, and I'm used to the old Nintendo games from when I was a kid, and I saw the new little micro cards that go in, and I'm like, wow, it used to be this big, huge cartridge, and now it's a little teeny tiny.
And then if you want the more storage, you have to get like a micro SD card to load into it.
I look at those and I go, boy, is that a money maker? Because it's like, Mom, I lost the game.
Oh, right.
I think it's in the vacuum cleaner. Oh, gotta go get a new one.
We just got a Switch a month or so ago, and I opened up the first box for the game and thought it was empty for a split second.
Because it's so little. Yep, it's pretty amazing.
All right, so computer files have this whole historical like background behind them of originally starting with tape drives, and that conceptual model still exists today. That as far as the computer, the operating system is concerned, that file is a tape. And you have to start at the beginning and roll your way towards the end. And you can't just randomly flit about without incurring a significant access penalty, time penalty. Even though today we have SSDs, which are essentially random access, right? It doesn't take any more time to go to block number 0 as it does to go to block number 1000 on an SSD. SSD is basically just basically slow RAM, high density slow RAM. So maybe someday in the not too distant future, operating systems will dispense with the distinction between a file and RAM. And maybe everything will just be RAM.
Yeah, random access. That'd be neat.
That you don't have to like save your work to a disk. It's just stored in memory all the time. It's going to take a complete shift in the way we write programs, but
yeah.
I mean, imagine like never having to open a file and close a file. You just declare an array and there's all the data.
Yeah. That would be, it's hard to picture that. It's hard to think about. It'd be neat.
Okay. For those of you who are wondering why the music is still playing, because I had to run an extra wire, and apparently that introduces an echo. But if I leave the music on, the echo goes away. So something's going on in the audio where if you have no background sound, the feedback loop starts. But as long as you have something playing in the background, it cuts out that feedback loop. Oh, someone asked, is that from an old teletype? Which one?
Over the paper.
Oh, could have been the paper. Somewhere in this box, I do have some old punched cards, but I couldn't find them in time. Nevertheless, and punch cards are not a good example of files because they weren't used for output mostly; they were used for input. It's just too complicated. Output would be like a teletype actually with paper in it. So punch cards were not a good output device; they were a good input device. Okay, so what's the review of all of the functions for dealing with files? We have fopen, and then what's the opposite of fopen?
Fclose.
Fclose. And how about some functions that can be used to get data from a file?
Fgets and fputs.
F.
Well, fputs doesn't get data, but fgets gets it.
Any others?
And fread.
Scanf.
F. Scanf. So these are input functions. And then how about output? You've already said some of them.
Yeah, fputs.
Fput-s.
Printf.
Fwrite.
Fwrite. Okay, so they're all basically the same functions we've used before, just with an F in front and an extra parameter that you pass in, but you use them just like what we're used to. So that's one of the nice things about a command line based computer system like this, is that the functions you use to send data to the screen are not any different than the ones you use to send data to a file. In fact, since on a Linux system, the screen and a file are just two instances of files, the screen is just called standard input or standard output, and the keyboard is called standard input. All the printf function does is just pass through its parameters to fprintf and then pass in standard out as the first parameter.
Oh,
Am I making sense?
Yeah.
Right? So it could be like, I don't know what the exact declaration for printf is, but it would go something like int printf whatever, right? And all it does is it calls fprintf with standard out as the first, and then passes in everything else. That's all it does.
Yeah, I know when I was using that in the 50 class, I was trying to, we hadn't learned printf in that, but we did it in here. So I was trying to teach myself printf, but the syntax was, using it was different. And now that makes sense. Like it wouldn't, instead of using echo, I was using printf to try to change the way I could declare the variables in it.
Yeah.
And it was printing out differently and I couldn't figure out why, but now it makes sense why.
And when you're doing shell, of course, you don't use like fprintf. You just use the redirection symbol to change where it goes to. Y'all on YouTube are being quiet. There was a lot of chatting at first. Now it's like, so let's do some sample programs. I want to write a program that reads in the contents of a file, converts everything to uppercase, and then writes out to a new file. Okay, so it's going to open a file for reading, read in the lines one at a time, convert each one of those lines to uppercase, and then writes it out to a new file. So we're using the same model that we were talking about last time, which is read one line from the file, process it, write it out. Read another line, process it, write it out. People who come from other programming languages like Java have a inclination or a tendency to maybe like open a file, pull it all into an array, walk through the array one element at a time, one string at a time, and then flush it all out to a disk.
Yep.
So that works, but as long as the files are fairly small, that's fine. But imagine if your files were much larger. You'd have to allocate that much memory. And really, you're only doing one thing to one line, and once you're done with that line, you're done, right? So you can do this alternating thing and save a lot of memory. Oh, the usual problem. What do we call this? Let's call this upcase. I think I already have a file called upcase, so I have to call it upcase file.
Upcase file.
Yeah. Someone's asking, like, can we use a buffer for that? You don't need to, because the operating system keeps a nice buffer for you. So even though you may think it seems really inefficient to go out to the disk drive, assuming it's an old spinning platter disk drive, and read one line and then process it and then write to another file, isn't the head going to be like going back and forth between reading over here and writing over here? And the answer is no, because the operating system sucks in a whole block at once. And actually, it probably doesn't pull in one block. It probably pulls in multiple blocks. Stores them all away into a buffer, and then you just work on that buffer, and then it flushes it out to the disk once in a while. So I wouldn't worry too much about the efficiency of even reading and writing one character at a time is going to be really efficient because it's all coming out of memory. It pulls stuff off of the disk once in a while. Okay, first of all, let's decide what file we're going to uppercase. I'm sure I have something in here, like this one, this hello.txt. We'll do that one. Okay, so let's open that file for reading.
We're still looking at your whiteboard.
Oh, sorry. Thank you. What do we do after we open the file?
You got to read it, right?
Before that. I think you missed this part last time. So.
We have to do the, what do you call it? The checking to see if it's actually there.
Yeah,
So
look do an error check, make sure it actually got open.
Yeah. The if statement for if doesn't equal, I'm getting that echo.
Remember this, so this is the idiomatic way to check to see if it returned a null. The more explicit way is to check if it's equal to null.
Mm-hmm.
But since the value of null is 0, this is probably the way you're going to see it. Okay, so we're going to print an error message. Can't open hello.txt for reading. And then we'll call p_error to have it display why it didn't work. And then we'll do the same thing for the output files. We're going to have both of them open simultaneously. Oh, oops, I forgot something over here. What am I missing on the fopen? I'm missing the mode. And then for the output file, what should I call this one? Hello up.
Caps. Hello
Oh,
up.
caps. Okay. And then I'm going to open that for writing. And then check to make sure it actually got opened. Oh, I keep forgetting over here. Sorry for those of you following along. You have to tell it where. I'm using fprintf, and I want this to go to standard error, so the error message goes immediately out to my screen. If I print a standard output, it's buffered. It's going to give it written to my screen when it's convenient to. But when I go to standard error, it goes immediately to my screen.
This is how we concatenate it, correct? With the standard error, so it'll print out the can't open, and then it will give the error reason why after, right?
Yeah, we saw that last time where I was using printf for my error message, but p error for the reason why. P
Okay,
error goes to
superseded.
standard error, and it came out first. Okay, now we're going to go into our loop. Whoops, I need a string. Let's call this line. We'll give it 1,000 as our maximum. And then we're going to use while f get s line 1,000 from the input file is not equal to null. Okay, remember that from last time. fgetS will return a null when it reaches the end of the file. So if we check that if it's not null, we know that we're still reading from the file. Okay, now we need to uppercase all the letters in here.
Just do that with a loop.
Yeah.
Just
Wait, how should we do this? We could do this with we could count from 0 to the length of the file, or length of the line. We could also use pointer arithmetic. Got a preference?
Pointer?
You want to do it with the pointers? So I do it like this. I go character pointer s equals line. Okay, so now s is pointing to the same thing line is pointing at, the first character of the array. So while s is not the null character, convert it to uppercase, and then, so I don't forget. I always forget this, right? Increment s. Okay, so I'm going to convert to uppercase. So I want to check to see if it's a lowercase letter, and if it is, convert it to an uppercase letter. We did this in a previous assignment, didn't we?
add 32 to it, right? Or subtract 32.
Subtract 32.
Subtract 32.
So we're going to say if the thing that s is pointing to is greater than or equal to a lowercase a, and the thing that s is pointing to is less than or equal to a lowercase z, then convert that. Can I do it like this?
Yeah. Yeah.
Someone on YouTube is asking, when I call this with 1,000, does it put the null character on there if it reads exactly 1,000 characters in? And the answer is yes, it does. When you put 1,000 in there, it actually reads 999 characters, leaving 1 for the null character. It ensures that there's 1 left over. So internally, fgetS is just subtracting 1 from that number, and that's the maximum number it actually reads. Okay, so we've zipped through the line, uppercasing each one of the letters as we go, only if it's a lowercase letter, and then when it reaches the null character, it stops and breaks out of the loop. So once we're done with the loop, I lost my place. Oh, write the line out to the output file. I think this is in the wrong spot. It goes here. Yeah. And then when we're done with that loop, the outer loop, then we can close the input file and close the output file. The question is, wouldn't we subtract 26 and not 32? If you look in the ASCII table, the difference between uppercase and lowercase letters is 32 characters. There's some intervening punctuation characters in there. Okay, let's save this, compile it. Uh-oh. What did I do wrong? Oh, I see what I did. Anyone see what I did?
Do you need to make line a pointer?
No, line is a pointer.
Yeah, okay.
So since it's an array up here, it's already compatible with character pointers.
Yeah.
So take a look at the warning here. Incompatible pointer type, passing a 3-character string to parameter of type file pointer. It's trying to tell us something. It's trying to tell us that it's expecting a file pointer, but we passed it a string.
Do you need to convert the parenthesis or the modulus s to the pointer?
No. fprintf, for all the f functions, the first parameter is what file are we reading from or writing to. Okay, so save that. Let's try again. Oh, no errors. All right, so we're watching over here. Here is hello.txt right here. And then we don't have a file called caps, but we should see one up here. Oh, I saw something blink. Is it there? There it is. Let's go look at it. All right. Here's the original one. Here's the new one. So that's how I'd write that program if I was kind of like doing it from scratch, right? Go through each one of the characters in the line, one character at a time, check to see if it's lowercase, and if it is, convert it to uppercase. If it's not a lowercase letter, it leaves it alone, moves on to the next one. There is a built-in function for doing exactly that. It doesn't work on a whole string, it just works on a single character. You still need the loop, but in here we can replace this with pointer s equals to upper pointer s. So it takes the character pointed to by s, converts it to uppercase, and then we're just storing it right back in the same spot. I don't remember what header file I need. Maybe the compiler will tell me. Ah, it does. It tells me this one. All right, so it works. So the to upper function checks to see if the letter is lowercase and then converts it to uppercase, returning it back to you. Any questions on that?
I have an error. And I think it's something silly. Undefined reference to main.
Uh-oh. Undefined reference to main. That means the compiler can't find a main.
But there is. It's right there.
So even though it's there, for some reason it can't see it. Because the compiler, being the simple-minded thing that it is looking for a standalone function called main. It can't be inside anything. So is there a possibility that you opened a curly brace somewhere and then didn't close it, so the main is now essentially inside another function?
Well, there's nothing above the main.
Oh, okay.
And the closing curly brace corresponds to the main curly brace.
And is it declared like this?
Yep. Yeah, it's a user bin ld/user bin/lib blah 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 blah. stdlib, right?
Yeah.
Oh, C type H. Wonder if I need that. You know what I think it was?
What?
I think that I didn't save it. It worked. Now I've got
Okay.
a whole bunch of errors.
That's better, right?
That is
But,
better. Yeah,
but one of
'cause
them
now,
one of them is not. Couldn't find main, right?
right. Now I can go through and fix the little issues.
Any other issues?
How did you fix that first error that you had about the incompatible pointer types?
Because I forgot to tell it what file to output to. So the compiler was expecting the first parameter to be a file pointer, the variable that points to a file that's opened up. But what I actually passed in was a string.
Okay, awesome. Thank you.
So the compiler says, whoa, there's a mismatch here. I'm expecting a file pointer, but you passed me a string. That's an error.
There we
Do I
go.
need a return 0? No, I don't. Even though main is declared to be an int, the compiler will put a return 0 in there for me because this is the main. If it was any other function, it would complain about no return type or no return statement. But because it's main, the compiler will throw in a return 0 for me.
Is it gonna read in the directory that I'm in?
When you run it,
Yeah.
Yeah.
Or is it okay? Because it's not reading the text is there. Let's see. Oh, because I capitalize it. No, I'm just dumb sometimes. I do silly things. I'm really good at telling it to the duck.
Oh,
There we go.
Was it this class on Tuesday, or was it the other class where someone literally, I mean, they didn't actually have a duck, but they were describing the problem to me. They went, oh,
I do that all the time.
I see what the problem is.
That's terrible.
I might have done that the other day. I'm getting
Oh,
pretty
I think,
good
yeah,
at
I think
that.
that was you. Yeah.
And I think we were talking about how I've got a. Let's see if I can show
Oh,
Mr.
it's the guy in the back that you talked to,
Yeah.
right?
Yeah, Mr. Michael Clark Duncan. There he is.
Yep.
He blesses my meal.
he-
He sits
is
over
he-
my table.
Is he holding your hot chocolate for you?
Coffee today.
Oh, God. For those of you who can't see, the people on YouTube can't see all the Zoom thumbnails. He's got what is that? Is that like a mannequin back there?
No, so years ago, back when I was in high school, one of my buddies worked at a movie theater back in my hometown. And so this is like keep in mind, it was like 2002. The Ben Affleck Daredevil movie came out. So that's the cutout for Michael Clark Duncan as Kingpin. And so years later, that guy's twin brother, I mean, we're all neighbors and stuff. We lived together in South Lake when we were 18. And so I ended up with that cutout. And then we ended up, keeping it around. So, I mean, this is like 20 years ago now, just keep it around as a novelty.
That's neat.
Kingpin is that slapstick comedy about bowling, is that right?
Mm-hmm.
Yeah.
No, Kingpin, that was Kingpin's the name of the character. He's the villain. Kingpin is the Woody Harrelson movie where he loses his hand, and it's Bill Murray, Woody Harrelson, Jeff Daniels. God, movie.
Someone asked, what if we don't write return 0 in main? What error would pop up? It won't pop up any error at all. As you've seen, I'm compiling the program with no return 0, and it's fine. If I put one in, it's also fine. So whether I put a return 0 in for main or not, the compiler doesn't care. Just for main. Terry, is it working now?
It is, yep. It capsed everything and worked great. Thank you. What was that 2 upper?
Mm-hmm.
Oh, right there. S equals 2 upper S. Okay. Instead of the, wow,
the
that's
contents
like
of that
super
function,
convenient.
The contents of that function is almost literally what we had there before.
Yeah.
Right, and a little if to make sure that it's a lowercase letter and then uppercase it. So notice that we don't actually, with 2 upper, there's I don't know what the word is, right? But when you see 2 upper, you think, oh, it's just going to subtract 32 from the ASCII value. So even if I pass it like a punctuation character, it'll uppercase that, but it won't. It has a little if in there to make sure that it's a lowercase letter. So you can just basically blindly call 2 upper on any character, and it will uppercase it only if it's a lowercase letter. If you pass it a uppercase letter, it won't touch it.
I like functions. I like to use them.
If they're well written.
Yeah.
So
right.
If the contents of this was just simply subtract 32, then
that wouldn't work.
You'd have to wrap it up with an if yourself.
Yep. I think it's because of my first learning language was Java. I just like functions. I like calling functions. There's so much. I mean, everything in that is, you call functions for everything.
Yeah. Definitely you want to break down your program into smaller pieces that can be individually tested and verified. That's a good thing. And don't worry about writing too many functions. The optimizer will take care of inlining functions that it needs to. It will leave functions not inlined if it's called infrequently. So I wouldn't worry about breaking. That used to be a worry 20 years ago. It's like, well, if you break it down too much, it's going to spend all of its time calling functions and returning from functions, and that slows things down. But these days, don't worry about that.
It's too fast, yeah.
It's not that computers are faster, it's the compiler smarter.
Oh, okay.
Right? Small functions just get their code pulled out of the function and stuck right into your program, as though the function call was never there.
Gotcha. Yeah, that's what we saw when you'd use that other program. Switching over to that website.
All function calls just go away.
Yeah.
If they're small functions. So this particular program only works for an input file called hello.txt and an output file called caps.txt. How can we change it so that we can just put those file names on the command line?
Put the argument into the main header.
argc and argv. I guess you'd have to add another one, right? Because you'd have to add a third argument for the output file.
So there's going to, what I want to be able to do is type in a.out and then hello.txt and then caps.txt, essentially. But I can put anything I want here.
Yeah, so you'd have to have in the main, you'd have to have the argc, the integer argc,
mhm.
and then you'd have to have the char argv, and then you'd have to have another argument.
No. So this is the way you declare main if you're going to accept command line arguments.
Oh, you can't do it
You can
any
only
other
take
way.
in 2 arguments in.
Ah, okay.
So
So
all
then,
those arguments go into this array.
so then you would just have to parse that array of argv and separate with like a space.
That's done for you. By the time your program is called, the shell has broken up the command line into the individual words and is passing those words into you in an array.
Oh, oh, that's right. It did that. We did that last time.
You know,
So
have
then,
you done shell scripting in your other class yet?
yes.
Yeah, so
yes.
you know, like $1, $2 for the,
Mhm.
right, those come to you already separated.
Gotcha. Okay. Well, then you would just call element 1 for that and element 2 for, yeah.
Whoa, whoa. I've run out of music. I was only expecting to have to play music for half an hour. I'm gonna start it over again.
It's actually really nice. I listen to music when I work anyway, so it's really nice having it in the background. But that's just me.
Okay, so, but my error message here is going to say hello.txt. How can I get it to put the actual name of the file there?
Put a %s there and then put the argv in the after the comma.
Uh-huh. And then do the same down here. And then the last thing we should do, since we're accepting command line arguments, is make sure they typed in those 2 file names. And we can do that before we even attempt to open the file. We should check to see if the value of argc is not equal to 3, then print out a message. Compiled, and we'll run it. This time, let's do a different file. Do I have another text file here I can work with? Here's one called strings. Oh, it's empty. Let's put something into it. That's not what I want. I don't know what that is.
That's the green egg. That's an amazing barbecue.
Oh,
You can do anything
It is
with
quite
that.
nice.
it's
is,
already
right?
it's already uppercased. That's not what I want. Oh, here we go. For those of you watching who are not in the United States, this is a very famous children's book. Probably every child in the United States knows at least part of this book by heart.
Oh, yeah.
And then the output file, we'll call it caps eggs. There it is, all in capital letters.
Mine didn't error, but it also didn't work. Oh, I know why.
It's always the little things, huh?
Yeah. I think this is why. I don't know. We'll find out. Oh no, because I didn't compile it. Oh my gosh.
It's always that. How could I compile this so that I don't have to call it a.out? I could call it like upcase. How do I change the compile line so that I can specify the name of the executable instead of using the default a.out?
Can't remember last time. I was like -O or I can't remember.
Yep, you're right, -O. So now
You only have to use the -O once.
yeah. So now I've got the executable called upcase, and then to run it, I can just say /upcase. And then let's test it out. Let's not put in one of the files here. This must supply a source and destination file. I just thought of something we could do. Okay, the word is no, actually this is not a refactoring. Let's redo this program a little bit so that if I don't put in the output file name, it puts it to the screen. If I do put in the output file name, it goes into that file. Okay, so if I run it like this, upcase greeneggs.txt, I'll see the uppercased file scroll by on my screen. If I do put the output file name, I won't see anything go by, it'll just go straight into that file. How do I do that? How do I start?
Set up an if statement, probably a little ways down after you open the file to check to see if you don't have what is it, 2 arguments, and then if you don't have 2 arguments, then send it to st out, hand it out.
So I do need to start by checking to see how many command line arguments there are.
Right. I would do it with like a Boolean type thing.
Yeah. So some kind of flag, right?
Mm-hmm.
That is letting us know where the output's going to be going. If there are 2 command line arguments, then we know we're going to go to the screen. And if there's 3, we're going to go to a file. I think what the other guy was saying is an improvement that we can make in just a moment here. But the kind of the more straightforward way to do it is some kind of flag that lets us know where the output's going to be going. So let's set up a flag. Let's call like
I called it 3.
call it 3.
3
No.
argument. Yeah. Two string. That's better.
Two screen.
I meant to say 2 screen, but I've said 2 string so many times that it came out 2 string. And
Okay, so if the number of arguments is equal to 2, then we'll set 2. I almost wrote 2 string. We'll set this to 1. and then we don't have to generate an error message for that. If argc is not equal to 3, oh, I erased the error message, so now I got to put it back in. Now that I've set that flag, I can now do something appropriate with it. Like here, where I'm opening the file for output, I'm only going to do that if I'm not outputting to the screen. So I'll wrap this all up with if not to screen, do this stuff. And then down here, where I do the printf, I'm just going to put an if-else there. If I'm going to the screen, I'm going to use printf, and if I'm going to the file, I'm going to use fprintf. And then finally, if I'm not going to the screen, go ahead and close the output file. Okay, I think that should do it. Oh, I've got a couple of errors. Where was that? Line 54 and 58. It's down here. So it doesn't know what to do with out. Where's that coming from? It says that out is not declared.
Is it because of encapsulation?
Mm-hmm.
Scoping?
Yeah.
Okay.
So
Do you see it?
Yeah, it's inside the if2 screen.
Mm-hmm. The declaration for out is inside of those curly braces for the if, and so if we're going to the screen, the value, the variable out does not get declared, and so we get the error. So we need to move this declaration outside. Oh, and then now this is now a file pointer, so I don't need to dereference it. There we go. Now let's try to run it. So if I just say upcase greeneggs.txt without an output file, we should, uh-oh. Uh-oh, it didn't work.
Well, because it's not, you have if it's not 3, and if you have 2 and it's always not going to be 3.
Oh, how
So
do I fix that?
Else if.
Yeah. Good. So these two conditions are dependent on each other.
Mm-hmm.
They're not independent of each other, so I need to put an else in there. Oh, good. There it is. And then if I do put the file name on there, nothing appears on my screen, and then caps.txt contains the uppercase text. That's good. All right, so that's a good solution. You check to see how many command line arguments there are, and if there's only 2, then you set a flag to indicate that the output's going to be going to the screen. If there are 3, the flag remains at the output is going to a file. And then sprinkled through the program are these checks to see if I'm going to be going to the screen, then I don't open the file. If I'm going to a file, I do open the file. And then for my printfs here in the loops, I check to see am I going to the screen or to the file, and I call the appropriate function. Okay, this is great. This works.
Mine worked. At the end, it said segmentation fault, core dumped. At the very last, after it printed everything, like it ran the program correctly, but then at the end it crashed.
Okay,
I just noticed that.
So you might be trying to close a file that's not open.
Yep, that's what it is. That's exactly what it is.
Remember over here, it allocates this memory, right?
Mm-hmm.
If you call close, it's going to attempt to deallocate that memory, but the memory doesn't exist.
Gotcha. Add another little if statement. There we go. Perfect.
All right. Okay, so the last thing I want to do before we take a little break is this. I hate all these little if-elses. Right? The program essentially is the same. The only difference is we either call this function or this function, right? Or we either open this file or we don't open the file, right? So we got all these little if-elses sprinkled through the whole thing. On a system like Linux or a command line environment, everything's a file. The keyboard is a file. The screen is a file. When your program starts up, there are 3 files already open for you. Standard in, standard output, and standard error. If we fprintf to standard output, it's just like calling printf. Remember I showed you on the screen over here. When you call printf, it's actually calling fprintf with standard out. So let me show you what we can do here. We still have to check to see how many command line arguments there are. But I'm going to do it like this. I'm going to take this declaration for out, and I'm just going to move it. I'm going to move it up to the top. And I'm going to initially set the output to be standard output. Okay? Now I don't need this Boolean variable anymore because now my output variable here indicates where it's going to go to. Okay, so if argc is equal to 2, let's see, let's do, we got to flip something around here. So hold on. If argc is equal to 3, oh, let me put that variable back in. There. I'm going to leave all this part the same here. Okay, so if we are not going to the screen, we're going to change the output destination to be this file. Okay? If we are going to the screen, the output destination is standard output. So down here, where we have these 2 printfs, I can just say fprintf to the output destination without having to check to see what the destination is.
Ah.
Right? If I opened the file, then the output destination will be that file. If I didn't open the file, the output destination will be standard output. And then down here, you know what I can do? I can just close the output. If it was the file, it'll close the file. If it was standard output, it'll close that, but then my program will exit, and then it doesn't matter. All right, so this should work. No compile errors. And then Here it goes to the screen. And then here it goes into the file. We're taking advantage of the fact that, at least on a Linux system or a command line environment, outputting to a file and outputting to the screen are the same operation. You just use a different file descriptor. And when your program starts up, there are 3 files open for you: standard in, standard out, and standard error. Those are already open for you. They occupy the first 3 slots in the 1,000 or so that you can open. All right, so
Yeah, that's neat.
so the question is, if we close standard output, can we open it again? No. No, actually you can. You can open a standard output. You have to open the file /dev/tty for reading. Oh, for writing, excuse me. But I wouldn't do that. Avoid closing standard output. I mean, unless you don't want your program to write to the screen at all.
So when you're doing passwords, does it just bypass that standard output? Is that how that works in Linux?
What it does is it talks to there's your program, and then it talks to the standard output driver. It sends a command to it that says, don't pass along any characters.
Gotcha.
Temporarily. So you can switch that on and off.
Okay, cool.
So when you're typing in passwords, it switches off passing through the characters. And then when you are done with the password, it flips it back on. You have to be really careful. You have to be really careful, because if you are writing a program like that where you switch off that and then you abnormally terminate your program, like you do Control-C or the program crashes, guess what?
It doesn't turn back on.
Yeah, standard output is still not passing through any characters.
Oh, no.
So in that case, you type in reset, and that tells it to reset the drivers.
Okay.
But you blindly type it. Right? You're not going to see it on the screen. So you just go reset and enter. And if all goes well, it'll like clear the screen, and then you'll get your prompt back, and you'll be able to type again. When I was in college, I did that a lot. Oh no, so what you have to do there is you have to catch those signals that are coming from the operating system. So if your program crashes, it sends a signal to your program that says your program's about to crash, right? We're about to be terminated. Or if you do a Control-C, it sends you a different signal. It says someone's about to stop your program. And then you can catch those signals, and then just before your program crashes, you quickly flip that back on.
Yeah.
And then
wow.
and then let it stop. Okay, we need to take a little break. Some of you have been here for an hour and a half. And then we're going to come back, and I'm going to introduce the assignment for this week, and it's about password hashing. Okay, so the Zoom folks, I get to hit pause, and then you never see the break. The YouTube folks, you got to sit through the break. It's about 10 minutes long. Right, so Zoom folks will be back in about 10 minutes, but you won't see it at all. It'll just go like that. Oh my goodness, I just realized, in all the excitement of streaming to YouTube, I forgot to hit record.
Oh no.
Ah, guess what? There's going to be a YouTube recording.
Yeah.
I'll just have to post that.
Yeah, I didn't think about that. I always hear that.
Yeah.
That's when I'm like,
totally
oh,
forgot.
okay, here we
I was
go.
like, at the last moment, I was like, let me set this up. Let me set this up.
Yep.
Right? I forgot to record. I hit go live on YouTube, right? But I forgot to record.
It's terrible.
See, someday I'm going to automate all this, right? But, I've got my Stream Deck here, so there will be a button here that just says, right now it says record, right? But the record will do both. It'll tell YouTube to start, and it'll tell Zoom to start simultaneously. If we
cool.
like this setup.
Can I ask you a quick question about the file search warm-up assignment?
Mm-hmm.
Do you want it to be so that, like, the string that the user is searching for, should it be able to be more than one word, or are they only searching for one word?
More than one word.
More than one word, okay. So you have to kind of make a loop with the arguments and put them into one big string and then search for that?
Wait, is it getting the word from the command line, or is it prompting?
From the command line.
Oh, then just one word.
Okay. Okay. Thank you.
I am gonna grab a snack. I'll be right back.
Hashing has not been mentioned. This is new, so don't worry, I'll give you a little background on it. Is this weekly? If you missed the first part of the stream, I'm trying a little experiment to stream simultaneously to Zoom for my students and then simultaneously to YouTube, in part to address the needs of a couple of people that said that they live out in the rural area and they can't watch the Zoom session at full resolution because their internet's too slow. But YouTube will nicely downgrade the bitrate to accommodate your bitrate, your internet connection. And so I figured, well, what the heck? I'll just try streaming to YouTube Live and see what happens. And I knew a few of you would show up. Because you all have sent me on notifications when I go live. I remember one time it was about 5 years ago. I mean, I hadn't streamed in a long time. And I accidentally hit the go live button. Accidentally. Click, oops. And then like 4 people popped in and said, you're live. What's going on? And then like 10 seconds later, the stream just cut off, right? Because I realized what I had done. Like, oops, sorry about that. Oh, so this particular class is Tuesdays and Thursdays at 9:30 Pacific time. We're going to spend the next couple of weeks talking about cracking passwords. Turning into professional password crackers. So I haven't had to deal with this in a while. What I need now is a splash screen that says like, be right back. But I didn't have time to set that up. So I don't have anything of the sort. So you just get to look at me. Or you can look at my, oh, here's what I can do.
I have one more question while we're not recording, if that's all right.
Yep. What's up?
Okay, I just saw you put a comment on my Making Change lab, and it asked how I came up with the algorithm for it.
Mm-hmm.
So I just saw that yesterday and answered it. I read a bunch of stuff and I watched a bunch of YouTube videos, but there was one video that was really helpful, so I put it on there.
Oh, cool.
So I hope that's okay.
Yeah.
Okay.
No, I wasn't like trying to like catch you or something. I just wanted to know where you got that.
Okay.
Yeah.
I was like, oh yeah, I got it here, and then I was like, oh man, I hope that's all right. Like,
No,
suddenly.
because I think I did say on that assignment, you will probably have to do some research.
Yeah, I definitely
Yeah,
did.
yeah.
I didn't know how to do that at all. Like, I had to do a bit of watching and reading to find it. So anyway, yeah, good. I'm glad that's okay. I was like, I wasn't cheating, right?
There is the echo. Can you hear it?
Yeah.
I don't know what's up with this echo thing.
You don't.
It's the jury-rigged, bodged audio.
Well,
Cable
I
had
mean,
to run.
I've never heard it yet.
Yeah, he doesn't hear it. Only Tiffany, you and I do.
Really?
Mm-hmm.
Yeah, I don't hear a thing. I've never heard any echo.
I actually hear the echo from you.
Mm-hmm. Me too.
Whoa, I heard it for the first time. I heard it
You
on
can,
TV.
you can hear
It's
it
awesome.
when there's no background music.
Mm-hmm.
When there's
That's really subtle.
there's
Club
silence.
now.
It could be something to do with my mixer. When there's no background music, it ramps up the gain on the other audio.
Mm.
And I turned up the music during the break, right? So we're actually hearing more of the echo.
Mm-hmm.
If I turn down the music, so what's happening is the echo is coming from the background music. It's being fed into that audio chain. So if I turn down the music,
Yeah, then the echo goes away.
echo goes away. It's there.
So-
It's just really quiet.
So what happens if you just turn the music all the way down?
I don't know. It probably goes
Now
away.
there's-
No echo.
Now there's no echo.
Oh, hey. All right. Well, that's the solution there.
Yeah. Until it ends, right? And then no, because it'll still be
No,
turned
as
down.
long as
That
it's
channel will
turned
still
down.
be turned down.
Yeah,
Yeah.
that channel's turned down.
I like the music personally. Having that in the background's nice.
Circus music.
Yeah.
Someone's asking, am I the one that did the DNS videos? That would be me, yes. Did you find them on YouTube or did you find them somewhere else? Because way back when I made those videos, I was approached by some, I don't know what organization it was, but they said, can we use your videos in our instructional materials? And I said, sure. I never got around to finishing that series of videos. And that was now at least 10 years ago.
Wow.
Golly, that was back when I was using a Wacom tablet with, not with the regular tablets, but with the screen. I was writing on the screen. Now I use an iPad to do the same thing.
Mm-hmm.
And then, what else was different? Oh, I didn't have a video switcher. Just using OBS to do the switching. And then you didn't see me on the screen at all. It was just a faceless voice. I was trying to emulate the Khan Academy videos back then, right? Because that was state of the art 10, 15 years ago, right? Everyone wanted to do like what they're doing. So I got the same thing, got the Wacom tablet, got the same software. You see the little plus cursor moving around on the screen.
Mm-hmm.
The same disembodied voice talking to you.
Mm-hmm.
Some people even said, you sound like Salman Khan.
Yeah.
Without the accent.
Mm-hmm. Yeah, that's what I thought when I was watching your Epsilon videos with the finite state machines.
Yep.
That was my first thought. That's why I even asked you if you did videos in Khan Academy.
Ah.
Because
Yeah.
you sounded like it. Like the, I don't know what you call it, nuances, I guess, of the way that you say it. And it just, it reminded me a lot of
the
it.
best. And then from there, I went to I started watching Twitch to see what they do, right? And I go, oh, they're doing like little green screens with a little person in the corner. So green screen goes up. And then there's me in the corner. And then we started doing Zoom stuff. So now you just see this. Because I don't want to hang a green screen here in the middle of my office.
Yeah, mine is, now that I'm in the new place, it's about 3 times the size of my old one. It's really nice. Lots more room.
Are you still in someone's bedroom?
Yeah, it's mine. It's my bedroom. But yeah.
You need some
It's
light
much,
on your
much
face.
bigger.
You need a little light on your face, right? A little washed out. You look a little sickly.
Oh, do I?
Yeah.
I haven't been outside much. I was when I first started the semester, I was running like all the time. Every day I'd run 5-6 miles. And then I've just been so busy with everything that I haven't been outside much. So it's probably that I'm just sickly looking. Because I've got, well, you know what, maybe this. Let's see. See if I can change it. Where's the button at? How about now?
Better.
Okay, so it's the light above me. I had it on like the high fluorescent light.
A little color in your face now.
I like running on a trail next to my house. It's kind of like through the woods. It's really nice, except that the last few days, people on Facebook have been posting that there's like this aggressive bear in our area, and it's like it's like huffing at people and it's eating everyone's chickens. And I'm like, I'll hold off on the runs for just a little while.
Yeah, that's creepy.
That's not great.
No, I grew up in Cool, kind of near Georgetown, if you know where that is.
Oh yeah.
And yeah, we had mountain lions out there,
Mm-hmm.
and so you'd hear about that occasionally, that somebody's cat got eaten by a mountain lion or
Yeah.
dog got attacked.
We have mountain lions and bears. I'm up in Forest Hills, so we have these things.
Oh,
but
yeah.
you know, and people spot them every once in a while, and it's not really a big deal. But when you have one that's been repeatedly like terrorizing people's yards
Yeah.
and livestock, I'm kind of like, oh, I'll wait.
I was staying at one of my buddy's houses up there, just before, or is it just after? I think it's just before Monte Vista Inn. And he had a bear go. He had 2 big, huge trees, and he had a bear go up one of them, a little cub go
Oh,
up one of them. So we knew there's a cub, there's going to be a big bear somewhere.
yeah.
So we got all the dogs inside and just hung out in the house until it was all done. But yeah, the bear pooped while it was up there. It was pretty funny.
Oh, nice.
Hit the ground and just exploded.
Just a,
Like,
just a
all right.
word of note here. You know, although we're normally on break, this is still streaming to YouTube.
Oh, sorry. Okay.
So I mean, like you can talk, right? But I'm just warning you, like, don't say anything that's like personally identifying.
Ah,
Yeah. So don't mention the name of your street or
yeah.
where
Yeah,
your kids go to school, anything like that.
I see. Whoops.
gotcha.
Oh, what's the UTC of this class? What is it? Well, it's UTC -7 while we're on daylight
Yeah.
savings time.
Right.
Then it would be UTC -8 in about a week.
Oh man.
A
2
week,
weeks.
really?
2 weeks. Well, a
Okay,
week and a half
dang.
ish, right?
Yeah. I hate that change. They just need to do away with it.
Yeah. I didn't really care about it until I had started putting kids to bed at a certain time, and then it was like, this is lame.
That's why I don't like it. Exactly why.
Also,
Yep.
also my pets don't know either,
Yep.
right? So
Oh yeah.
instead of waking me up at 7 in the morning, they're waking me up at 6. They're like, time to go.
Yeah.
It's still the same darkness outside, right? Time to go.
Yep.
Yeah.
That's funny.
I used to. Oh, never mind.
Should I put the music back on? The music there before.
Sure.
Really quiet,
Hmm.
so we don't get the echo.
Yeah, that's I put on progressive house when I'm either that or this station that's called, it's a bad name, but it's got really great music. It's called Two Steps from Hell. And it's like, it's all orchestration music. It's all orchestra, but it's the kind of music that you'd hear like at the end of a movie during the credits kind of thing, right? So it's like intense, but in a good way.
Yeah.
And I don't know how to explain it, but that's what I listen to, either that or progressive house like this when I'm working, because there's no words.
So some of you have already looked at the first assignment to do this week called File Search. It's a program that takes in 2 command line arguments. The first one is a string, just a single word. And the second command line argument is the name of the file to search through. This program basically works like grep. Right? You give it a string and then a file name. And then it just searches through that file, and anytime it encounters a line that contains that string, it displays that line. So that's all this program is going to do. It's just a grep clone, basically. So you're not going to display the string that you found. You're going to display the whole line that you found that contains the string. You may assume that no line is longer than 255 characters. It wouldn't be very much use to display the string that you found, right? Because you know what that is.
Yeah.
There's an optional extension on this. You could pass in a -I flag to mean you want to do a case-insensitive search. So it doesn't matter whether you enter a lowercase or an uppercase string, it'll find it in the line.
Just like grep.
Just like grep does, yep. So you're going to want to like look through the argv array to see if that flag is there. And then if it's there, set some kind of Boolean in your program to indicate you're doing a case-insensitive search. How do you do a case-insensitive search? There is no string function to do a case-insensitive search.
Would we set it up like we did today, where we kind of just copy everything to uppercase on both sides and then compare it, or is that too many steps?
Great. Yeah, right. So basically you take your target string that you're looking for, convert it to uppercase, take the string out of the file, convert it to uppercase. Now everything's in uppercase, and then you can do your string matching on that. So like 2 extra steps. Yeah.
I think, is it a big program to, I've been trying to think about it. I think that I want to do my CSCI 50 final project as a Git pushing program.
Oh, okay.
Do something like that. I think that would be fun.
So we're starting a new unit where we're dealing with passwords and how passwords get stored on a system. Brief introduction. When you go to a website or you go to something where you have to sign up for an account, it asks for your information, but most importantly, it asks for something like a username and pick a password. So something that identifies you and then something that authenticates you. Then it has to take that information and store it in a database of some sort, whether it's just a file or an actual proper database. It doesn't matter so much, but it stores the username in the clear, which means it's just plainly visible, and then it stores the password right next to it, probably on the same line, or if this is a database, in the same row on the table. But if you're a good website operator, you're not going to store the password in the clear either, probably for some obvious reasons, right? You know, the most obvious reason would be if somebody gets a hold of that database or that file, there's the usernames and passwords right there, plain as you can see. So you want to take the passwords and you want to do something to them so that it's not obvious what they are. So there's 2 things you could do. One is you could encrypt the passwords so that every time someone logs in, you just temporarily decrypt the password, check to see if it matches, and then re-encrypt it. That's not a good solution because the key to lock and unlock the encryption also has to be on the computer somewhere. You're not going to have a human typing in the unlock password every time someone wants to log in. It's just not going to happen. So the encryption and decryption key has to be on the computer somewhere. And again, if somebody is able to obtain that key, they can now decrypt all the passwords. So the third technique, and this is the one that's actually used, is called hashing. It's kind of like a bit blender. You take the data that you want to run through this blender, you pour it in, and then it churns up all the ones and zeros. And what comes out is a jumbled up mess of ones and zeros. And there's two important things about this blender. One is, if I was to pour the same data in again, I would get the same data out. So the blender is not a randomizer. It's a mixer, but it mixes in a deterministic way, so that I will always get the same output for the same input. The second thing about this blender is that no matter how much data I pour in, I always get the same amount out. Meaning, like, if I pour in 100 bytes of data, I'll get, let's say, 10 bytes out. If I pour in a megabyte of data, I'll get 10 bytes out. So it's kind of like a coffee grinder. You pour in a cup of coffee beans, but you only ladle out the tablespoon that you actually need to make the coffee. You can pour in a bucket full of beans, but you only pull out the tablespoon that you actually need. Throw the rest away. So unlike encryption and decryption, hashing is not reversible. I can't start with that tablespoon of coffee beans and go back to the original bucketful. Because I threw away most of the bits. The ones that I kept, I mixed up, but I threw away most of them. Okay? So you can't, unlike encryption, which you can reverse, hashing you cannot reverse. You can't go back to the original text from the hash. There's no direct way to calculate what the original was from the hash, because, and the reason why it's called hash is because it's like, you know, the American, like, you know, take a potato and chop it up into a bunch of pieces. It's hash, right? That's why it's called that. So there are a variety of algorithms for doing hashing. There's an older one called MD5. There's some really old ones that we no longer use at all. But there's an old, this is the MD5 is probably the oldest one that's still in common use, although it's discouraged from being used. There's SHA-256, SHA-512. There's one called bcrypt. There's a few other algorithms out there that are in common use, but these are the ones you're probably going to run into most often. MD5 always produces a 128-bit output. Always 128 bits. No matter how much data you pour in, you always get 128 bits out. SHA-256 produces 256 bits of output. You can probably guess what the next one produces.
511. Just kidding.
512 bits, and bcrypt I think is 184. If I remember, 184 bits. But the point is, it's always a fixed size of output, no matter how big the data is going in. So like over here, I've got this file called The Complete Works of Shakespeare. It contains all those poems and sonnets and plays. They're all in this file. You can download this file off the internet. And if I run it through one of these hashing algorithms, you'll see I'll get an output. So if I go MD5 of Complete Works of Shakespeare, I get this. This is the 128 bits of output represented in base 16, just so it's nice and compact, but it's 128 bits. The actual input file is 124,000 lines of input. Actually, let me run that without this flag. We can see it's 124,000 lines. It's roughly 9 million words and about 5.4 million characters. Actually, this is one of the interesting things about this Complete Works of Shakespeare file is this file represents the sum total of one man's output back in the, what, 1500s, whenever he lived?
Yeah,
Right?
that's crazy.
So it's a 5.5 megabytes is his life's work. And I can take a picture on my phone and it's about the same size.
Yeah.
And it represents 1/100th of a second of my life.
Yep. Wow.
So big difference in the amount of data that's being produced by us today versus someone back then. You know, and he was an outlier, right? You know, this is someone who wrote professionally. You know, what was the output of the average person?
Sure.
Most people were illiterate.
Yeah, I was just gonna say
you know,
that. Zero.
You know, yeah, close to zero. You know, maybe a page or two.
Yeah. Wow.
So if I if I run this file through this hashing algorithm, I get this string of output. If I run it through one of the others, 256 Shakespeare, I get, you can see a string that's twice as long because it's got twice as many bits as output.
Mm-hmm.
And then if I run it through the other one, 512, see it's even longer than that.
Mm-hmm.
But they're just a string of ones and zeros. Then if I go into that complete works of Shakespeare and I like pick a line, like go to like line 80,000 or something, and just change one of the characters in there. Like let's change this O to a P right there. I've essentially, by just changing one letter to the next letter in the alphabet, I've essentially just changed one bit in that whole file, essentially. And then if I run it through the same hashing algorithm, if you compare this to this,
Yeah, completely different.
it's completely different, right? So it's not even close. And that's important also, that it doesn't give you any information about where the problem occurred. It just tells you that something's different about the files. So same thing with passwords. When you set up an account on a website, it stores your username and password in a database. It hashes the password, so it turns into this string of hexadecimal digits. Then when you log in, again, when you come back to that website, you enter your username and password, then the system takes the password that you typed in, hashes it using the same algorithm, and then compares the hash that it came up with then against the one that's in the database. If they're the same, then it can be reasonably certain that the password matches what you originally set it up with. And if they're different, you know there's a mismatch of some sort. You don't know where the problem is, you just know the passwords are different. So there's no information here about where the problem is. You don't know if you're close to finding the password. So that's all the system does, is it just hashes the password that you entered the second time, compares it against the hash that's stored in the database, and if there's a match, it knows the passwords likely match, and if they don't match, it knows there's a difference. That's all there is to it. And when I say by it's likely they don't match, it's because there is a very, very small possibility that two passwords might hash to the same value. Okay, for MD5, it's a 1 in 2 to the 128th power chance. There's 2 to the 128th bits, or 228th possible hash values for MD5. For SHA-256, it's 1 in 2 to the 256. And so MD5 is not used so much these days because these hash values are fairly small, relatively speaking. The one that's more commonly used is this one here. And one of the reasons is 2 to the 256 is what scientists think is roughly the number of atoms in the known universe.
Yeah, 10 to the 77th.
Yeah, which you convert to base 2 is
Yeah,
somewhere in
that's
that
huge.
ballpark.
Yeah.
So it's kind of like saying, here's an atom right here, somewhere in the universe, there's another one just like this one. Go find it.
Yeah.
Right? You might find that. You might get lucky. It might be right over here. But chances are it's somewhere in a different galaxy. You'll never find it.
Oh, that's a big number.
And then for Shay 512, I mean, now we're talking about for every atom in the universe, there's a whole other universe to search through.
Yeah.
So here's an atom in this universe. Somewhere out there, there's 2 to the 256 universes, and each one of them contains 2 to 256 atoms. Go find the one that's identical to this one.
Yep.
Yeah. People are saying, like, you know, how can you break the hashes? What you need to do is, and this is what we're going to be doing in this class, is you can't reverse the hash. What you have to do is brute force them. You have to start with a candidate password, something you think is the password, hash it, and then see if it matches. And if it doesn't match, move to the next candidate. So you could brute force it by trying all the passwords, starting with A, and going to Z, write a whole bunch of loops that'll just loop through all the combinations, hash each one of them, and see if it matches. What I'll talk about next week is humans don't pick passwords like that. If you're using a password manager, you do pick passwords like that, but if you're just prompted to type in a password, you're probably going to pick a word. And that's how our password cracking program is going to work, is it's going to have a dictionary of words to try. It's going to hash each one of them, see if it matches. And if it does, bingo, you found it. So we're going to write, I think, a total of 3 programs. A total of 4, actually. The one we're going to write this week is just to get practice hashing, just to be able to do this. And then the first one is going to be able to crack, I think, a single password. The next one will be able to crack using a dictionary. And then the fourth one, the next one after that, is going to be able to use a dictionary, but the dictionary will be much, much bigger, like with 3 million words in it. And you won't be able to just loop through the dictionary. It's too slow. So you have to build a data structure. When you build a data structure, you can search that dictionary really fast. There are programs out there to do this for you. There's one called Hashcat. It uses your GPU, if you have one, and splits up the work among the hundreds or thousands of little processors you have. I might do a demo next week, showing this program running on a system with 5,000 GPUs, 5,000 processors in the GPU. See how fast it goes. Anyway.
That was neat in 26 when you did that.
The same demo, exact same demo.
Yeah.
Okay, so I want to write a program that just prompts the user to type in a string and then just hashes it. So basically, I want it to do this, but for a single word. And in fact,
all we can see is your face.
I wanted to just produce the hash output. In fact, there's a website you can go to called Cryptii, C-R-Y-P-T-I-I, yeah. And if I change this, whoops, if I change this to, where is it, hash function, and then I choose MD5, and then I tell it to display it as bytes with no grouping. Then if I type in hello, I get this as the output. If I type in hello with an exclamation mark, you'll see the output completely changes. I added one character to the input string, and the output completely changes. So basically, I want to write a program that does this. Right? You type in a string, it gives you the output. Okay. So to be able to do this, I have to give you some library functions. There is some built-in functions for doing the MD5 hashing, but they're a little difficult to use. And so I've written a wrapper library around that, where you just got one function called MD5, and it just does the work for you. I forgot to prepare for that and copy the file into my environment. So I have to go and find that file and drop it in there. So give me a moment to go and find that file. Hey, you're just looking at me while I copy this file. Okay, so there's two files that you'll need to do this assignment. One's called md5.c and one's called md5.h. The only one that you really need to look at is md5.h. It just tells you the function prototype. We've got a function called md5. It takes in a string and its length. So you got to pass in both things, a string and its length. And then it returns to you a string. And then when you're compiling this program, you need to link to the crypto library. So let's write a program that just simply prompts the user to type in a string, it hashes it, and then just displays it to the user, right? So it's essentially going to do what this website does. Why is the MD5.h in quotes instead of the angle brackets?
Because it's a function, right?
No?
It's frustrating because you told us and I don't remember.
Because it's in my current directory, not off in one of the compiler directories.
Ah, that's right.
So for user-supplied include files, quotes. For the system-supplied ones, angle brackets. All it does is it tells the preprocessor where to go look for this file. Okay, so we're going to prompt the user to type in a string, we're going to hash it, and then just display the output on the screen. So we're going to need a, we're going to do a prompt. Enter a string to hash. We'll use fgetS to get the input, because actually I want to be able to type in more than one word. I want to be able to type in a phrase and have it hash that.
We need to declare a...
Yeah, so we need to go like character, I'll call it plain, okay, because this is the plain text versus the hashed text. The plain text is the one that you can just see plainly, and then there's going to be the hashed text. So we'll call this plain. Let's give it a total of 100. Sounds like a good length. So we're going to type in that password. Remember, when you use fgetS, that new line character is going to be on the end. We want to get rid of that. So we'll use the one we learned about, the string searching function that looks for the new line character. it'll return to us a pointer to that character if it's there, and it'll return a null if it's not there. So if it's not a null, change it to a null. Okay, so this is going to trim off new line character, if present. Okay, so we've turned off the new line character. Now we need to hash it. So according to this header file, there's a function called MD5. You pass in the string you want to hash along with its length, and then it returns to you the hexadecimal string of hex digits. So we'll go character pointer hash equals MD5. We'll pass in the plain text along with its length. And you may be wondering, why do we pass in the length when it's just a string and strings are already terminated by the null character? It's because MD5 actually doesn't work on strings. It works on arrays of bytes rather than strings. You could just pass it in like an image, right? Which isn't a string, but you could hash an image. Mm-hmm. And so that's why we have to pass in the length, because there might not actually be a null character on the end of it. And in fact, the actual function that's working in the background doesn't look for the null character at all. It uses the length to determine how long the array is. This is what the file looks like. This is why it's complicated to do. There's all this other stuff to do. Mm-hmm. I wrap that all up in a nice, clean, one function to call. Okay, so we got our string back. Notice we don't have to allocate space for the string, because inside here is a malloc. Mm. And there's also a little tip inside the header file that says the 33-byte string is malloc by this function. The caller must free it. Okay, let's go ahead and print it out. And then to free up that memory that our MD5 function had allocated, we just call free. And then it releases that memory back to the operating system. All right, we're ready to compile this. There's two files we have to compile together. There's our hashword.c that we just wrote. There's the md5.c that also has to be compiled in, and then we have to link to the crypto library that provides the back end for all the hashing algorithms. So we're going to go clang, the name of our program, which is hashword, md5.c. Let's output it to hashword, and then link in the crypto library. Someone asked, is it good to set the pointer to null after doing a free? I suppose you could if you wanted. I don't worry about that. If you try to free it again, it's going to crash either way. If you try to free it twice, it'll crash. If you try to free it after making it a null, it'll crash. So it's going to crash either way. Uh-oh, we got a couple of warnings. So this first one can be fixed because I didn't include the string header file. Let's see, the next one, free is inside of the standard library, so I need to include that. I think that'll take care of it. And by the way, if the compiler says you're missing a header file and you don't know which header file it's supposed to be, the thing I do is I go search for that function. So I type in something like C and then free. And then usually it takes you to something like tutorials point or CPP reference. And then it should say right up at the top, here's the library you need to, or here's the header file you need to include. So that's what I do. If the compiler doesn't tell you right off the bat what it's supposed to be, then a quick Google search will tell you what it is. Oh, I ran out of music again. We're almost done. We'll just start this over. Okay, save, compile, good. Hash word, enter a string to hash, hello. Okay, I got 8B1A9953, and then the rest. Let's go compare that to what we came up with here. Look at that, 8B1A9953. That's, I just look at the first few. And that's the same, right? It ends with D7 over here, and this ends with D7. So I'm pretty convinced that this is working correctly. Let's try putting in hello with an exclamation mark. And we get this one, 952D2C5. And if we go over here, put on the exclamation mark, we get 952D2C5. This is the same hash. And then finally, let's put in a phrase. And what did we get here? 86FB26. Come over here and put this one in, and we get the same thing. So this is a very simple program that shows you how the hashing function works. Pass in the string along with its length. It'll pass back to you a string. It'll just give you the pointer to the string because behind the scenes it's doing a malloc. You can do whatever you want with it. In this case, we're just printing it out, and then you free it up in order to reclaim that memory.
Where do we get the MD5?
Let's see.
Is that under files? There's a small file here under files.
So on the assignment page,
Yeah.
there's
Cut and paste it?
Yeah, just copy and paste them.
Okay.
Let me close this. We don't need that anymore. Don't need this anymore. There we go. In the future, I'm going to give you those files in a Git repository. So you'll just be cloning a repository that I've got for you. It's already got the starter files, and you just modify from there.
Cool.
But for this one, copy and paste, put them in your directory. Okay, so the assignment itself is not to hash a single phrase. It's to open a file for reading, read each line of the file separately. We've got lots of practice doing that. Hash each line of the file, and then display the corresponding hash. So if this is the input file that you've got, you should see these 6 lines as output. If you don't see those 6 lines, something's wrong. It doesn't tell you what's wrong, but something's wrong. Here's another input file.
8 o'clock yesterday. It was very time consuming.
Did you hear about the monkeys who shared an Amazon account? They were
That's funny.
primates.
Yep.
2 guys stole a calendar. They got 6 months each.
A crocodile for a thieving alligator. That's funny. My daughter will like those.
There's a Twitter account called Dad Jokes. I got them all.
Yeah. Nice.
So if this is your input file, then you should get these 5 lines as output. Okay, and then that'll get us started towards what we're doing next week, and the week after that, and the week all the way after that, where we start writing these programs to crack passwords. So I will essentially, to give you a little preview, I will give you a file that has a whole bunch of hashes in it, and you need to figure out what those are. So I'll give you a file with a bunch of hashes. I'll give you a file that has a whole bunch of candidate passwords, and you're going to try each one in those files and see which ones match. You're guaranteed to find a match. Every single one of them came from that file. So if you don't find any matches, something's wrong with your program. You will find a match for every single one of them.
Cool. That'll be fun.
All right. Yeah. Okay, so it's noon here on the West Coast. We're enjoying the rain.
Yeah. Finally.
And this is the first of two. The next one's coming tomorrow. Although I'm thankful for all the rain we're going to get, I'm a little concerned about the people that are a little further north, up where it burned.
Yeah. Yeah, I get a lot of mudslides with that.
Oh, someone says, let's try creating the MD5 algorithm. You know, there are plenty of places where you can just get the source code to the MD5 algorithm. And I've actually thought about that for this assignment, that instead of having you link into the crypto library where the actual algorithm is implemented, I would just give you the C source code, and you can see it's basically a blender of operations.
I started doing one like that in Java. That was fun. It was a little bit tougher in Java.
Here's the one in... Oh, the one in... What? The C one just says... Oh, now it shows it to me. But here's the blending operations. It's doing things like bitwise ands, where it's taking two input bits and then doing an and between them to produce one single output bit. So here's the important thing, like 2 bits go in and what bin comes out. So already it's throwing away half the information and transforming the other one. There's this tilde here is, what is that? Oh, it's a bitwise not. So it takes all the ones and zeros and flips them to zeros and ones.
That's cool.
This is exclusive OR right here, this little ampersand. Again, 2 bits go in and 1 bit comes out. Here's an OR operation right here. 2 bits go in, 1 bit comes out. So already all sorts of bits are being thrown away. So those are the mixing functions right there. And then it also goes through these rotation functions where it takes bits and shifts them left and right by these amounts. So not only is it doing ands and ors to transform the bits, it's moving them back and forth, almost, again, almost like a mixer would. And then there's a whole bunch of loops, and what it's doing, again, to use the mixer analogy, is just running the blender for, let's say, 1,000 whirrings of the blade. Right? And it runs it through the mixing functions, it runs it through the shifting functions, and it's just like a blender, right? You're moving stuff around, flowers flying into the air, right? You know? But this function is actually built into the standard library, the crypto library, and so I don't have to provide the source code for it. But, you know, you can look at it if you want. And since this is the Rosetta Code website, there are implementations in C, C#, C++, Forth, Basic, Java. The Java one, of course.
Oh man.
No, it's. Do you know why it's short? Why is it short? Just call the built-in one.
Oh, yep.
That's kind of cheating, right? You just import Java security message digest.
Yep.
That's not really like what I wanted to see. I wanted to see an actual implementation of the algorithm, not just a call to the built-in one. What's another one you might recognize?
Python.
Python. Yeah.
70.
Hopefully it doesn't just call the built-in one. Of course, it just calls the built-in one. Just import hashlib. That's cheating.
Mhm.
I mean, this would be useful to know how would you call that function if you were just calling the function.
Mhm.
You know, you want to know what's the correct syntax for calling it and getting results back. That's fine. But if you want to actually see what an implementation of the algorithm looks like in that particular language, this is not what I'm looking for.
Nope.
Oh, let's see. So someone's saying, like, you know, do I stream every week? I just started this week. I just thought I would do an experiment and see who would show up. And here you all are. Yeah, it's Tuesdays, Thursdays, 9:30 in the morning Pacific time. But on November, first week of November, first Sunday, second Sunday, I don't know the rules anymore. My phone takes care of it for me.
Yep.
Yeah, once my phone takes care of it, then I run around the house changing all the other clocks.
Yeah, same here.
Whenever that changes, then the UTC offset changes by 1 hour. All right, well, that's it.
Cool.
I can't guarantee that I'll be streaming every week. Sometimes we talk about things that are, because this is a live class, an actual class, we talk about things that are related to the class. And then I can't stream that. Privacy, blah, 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 you know.
Mm.
But I'll try. This weekend I'll redo the audio so we don't get that annoying echo.
But just keep the music playing in the background.
Oh, well, but the echo is still
Nice.
there, right? If the music gets really quiet, you can still hear the echo. I want it, you know, the perfectionist.
No, I know.
wants to just get rid of the echo.
After you fix it, just we'll still do
Oh,
the music.
still keep the music, just the
Yeah,
echo will be
I
gone.
really, really like that. Do you like that, Tiffany? The music in the background?
Yeah, I do for the class.
Yeah, that's really nice.
So Twitch-like, right?
It kind of is.
Oh, someone's watching from Brazil.
Oh, nice.
It's 4 p.m. there. Everyone's here because of the Makefile video. I think that is honestly one of the best videos I've ever made. Yeah, it doesn't surprise me that YouTube is not hearing the echo because your audio goes right through one device and straight to YouTube. It doesn't pass through a cycle of equipment like the Zoom people are hearing. Because the Zoom has to go through the equipment, come back into my computer, go back out to the equipment, go back into my computer, so it's just set up for some kind of cycle in there. Watching from India, where it is 2:30 in the morning. Wait, was that the start time or is that the time it is right now? Because you know what? Did you know, as Americans, did you know that there are some parts of the world that don't do daylight savings time? They just split the difference.
They
You mean
split it like
still,
it's half
yeah.
an hour?
Yeah,
do you mean
half an
split
hour.
the
They're just half an hour.
Oh,
what the
wow.
heck?
So this person says they're
Interesting.
watching from India, and right now it's 12:34 in the morning.
Oh, yeah.
That's half an hour. Well, it's 11 and a half hours off from us right now.
Mm-hmm. That's interesting.
Let's see, Pakistan, it's currently 12 in the morning. Yeah, let's hear from everyone. What time is it where you're watching? Someone else is watching from Morocco, where it's 8 o'clock in the evening. Germany, 9 o'clock in the evening. It was about 8 or so years ago, maybe 7 years ago, I realized I had a global audience when somebody was watching my live stream and says like, you know, it's really late, it's 4 o'clock in the morning, I need to go to bed. I'm like,
Wait, what?
Yeah. You must be in Europe somewhere. 10 hours forward from me. Let's see, yeah, Brazil, 4 in the afternoon. So yeah, we got Pakistan, Morocco, India, Brazil, Germany, and of course, United States. Switzerland. Yeah, the video will be up afterwards. Same URL. Do you think I should do this more often? Those of you who are watching over here. I'm looking over here because my Zoom people are over here. My YouTube people are down there. Okay.
Mm-hmm. Yeah, it's cool.
Greece, 10 o'clock p.m. Which books are there behind me? Oh, golly. Can I do that a different day?
Yeah, he talks. He's got a whole story about those.
Yeah. Okay, well, I think we're done for today. And of course, since I'm not a professional YouTuber, I don't have outro music. I don't have a thanks for watching screen. It's just gonna cut off. Here's someone else from India where it's just 12. Oh, it is 12:30. Yeah, so that's half an hour difference. Okay, well, that's it for today.
Alrighty. And I will see you Tuesday.
Okay.
Have a
Take
good
care.
weekend.
You too.
Thanks.
Bye-bye.
Bye-bye.
Bye, everyone on YouTube. Yeah, I'll do this more often, so I think I had a lot of fun. Right. Bye-bye. Oh, what can I do? I can do this.